This is SpaceTime Series 21, Episode 33. Coming up on SpaceTime, the most sensitive ever dark matter search gets underway, one of the ways humans touch the edge of space, and studying the Milky Way's gamma-ray skies. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists have begun their most sensitive ever search for a possible dark matter candidate known as the Axion. Dark matter represents one of the biggest mysteries facing science today. Although it appears to be invisible and can't be detected by modern scientific instruments, researchers know dark matter exists because they can see its gravitational interactions with normal matter, providing the additional mass to prevent galaxies from flinging apart as they rotate. Based on astronomical observations, dark matter makes up about 84% of all the material in the universe, meaning virtually everything we can see in the cosmos, from galaxies, stars and planets, right through to cars, buildings and people. All the so-called normal, or as physicists call it, baryonic matter, all of it comprises just 16% of the total amount of matter that makes up the universe. And from a scientist's point of view, that's a very incomplete and consequently unsatisfying picture of the cosmos. Now, as we've mentioned many times on this program, physicists have already come up with heaps and heaps of possible candidates to try and explain dark matter. And the front runner still remains the WIMP, weakly interactive massive particles, new yet to be discovered subatomic particles such as the hypothetical sterile neutrino. Until recently, the other big candidate were MACHOs, massive compact halo objects, things like huge populations of quiescent black holes and neutron stars, or heaps and heaps of giant planets and brown dwarfs. But that's fallen well out of favour recently. In fact, despite decades of research into possible MACHO and WIMP candidates, scientists have repeatedly struck out. The other subatomic particle considered a popular candidate amongst physicists is the hypothetical Axion. The Axion's receiving a lot of attention because its existence would also solve other problems with the standard model of particle physics today, including the fact that the neutron should have an electric dipole moment but doesn't. Like other dark matter candidates, Axions, if they exist, are everywhere, but they're extremely difficult to detect because they're so weakly interactive with everything around them. Because they interact with ordinary matter so rarely, they stream through space, even passing right through the Earth without touching ordinary matter. Of course, they wouldn't be unique with that quality. That's a description which also fits the neutrino. Be it tau, muon or electron, neutrinos are an extremely weakly interactive particle. In fact, there are billions of them passing through you right now and you don't even notice them. And they're very hard to detect, requiring special laboratories. And the same goes for the Axion. To try and detect this elusive particle and hopefully move it from hypothetical to real, and in the process solve the mystery of dark matter, physicists have just started using a new instrument called the Axion Dark Matter Experiment, or ADMX, which has been built at the University of Washington, Seattle. The ADMX is an Axion haloscope, essentially a large low-noise radio receiver, which scientists will tune into different frequencies and listen to try and find the Axion signal frequency, if it's there. Now, as we've mentioned, if they do exist, axions almost never interact with matter. But with the aid of a very strong magnetic field and a cold, dark, properly tuned reflective box, the ADMX will be able to hear photons created as axions convert into electromagnetic waves inside the detector. Think of it as a sort of old-fashioned AM radio. You're looking for a radio station, but you don't know its frequency. So you have to slowly turn the knob while listening until the station finally tunes in. If none of that makes sense to you, you'll have to ask your parents. A new report in the journal Physical Review Letters claims the Axion Dark Matter Experiment is the world's first and only observatory to have achieved the necessary sensitivity to hear those telltale signs of dark matter axions. That is, if they really do exist. This unique milestone is the result of more than 30 years of research and development, with the latest piece in the puzzle coming in the form of a quantum device that allows the Axion Dark Matter Experiment to listen for axions more closely than any other experiment ever built. And it's this feature which allows scientists to embark on the most sensitive search yet for axions. One of the keys to this experiment are low-noise superconducting quantum amplifiers, invented at the University of California, Berkeley some 2 decades ago by Professor John Clark. Now, we've spoken about Clark before, both on SpaceTime and its predecessor, Star Stuff. He was a pioneer in the development of sensitive magnetic detectors called superconducting quantum interference devices, or SQUIDs. Clark's high-frequency, low-noise quantum squid amplifiers are best known for reading the superconducting quantum bits or qubits used in quantum computers. But adapting the dark matter experiment to handle the squid amplifier was a complicated and difficult job. Still, Clark says tests have now shown that the experiment does work as advertised. Although located at the University of Washington, the Axion dark matter experiment is actually being managed by the US Department of Energy's Fermi Lab, the Fermi National Accelerator Laboratory in Illinois. The experiment's operations manager, Andrew Schoenschein from Fermi Lab, says if dark matter axions exist and they're within the frequency band the experiment will be probing over the next few years, then it's only going to be a matter of time before they're found. So, how does it all work? Well, the Axion dark matter experiment employs a strong magnetic field and a tuned reflective box to encourage axions to convert to microwave frequency photons. It then uses the quantum amplifier, the SQUID, to listen for them. All this is done at the lowest possible temperature in order to reduce background noise. Clark learned of a key stumbling block to the experiment back in 1994 when meeting with the project's chief scientist Leslie Rosenberg from the University of Washington and with Carl Van Bieber, who was head of UC Berkeley's Department of Nuclear Engineering. Because the axion signal would be incredibly faint, any detector would have to be extremely cold and quiet in order to pick it up. Noise from heat or thermal radiation is easy to eliminate by cooling the detector down to about 0.1 Kelvin. But eliminating the noise from standard semiconductor transistor amplifiers proved difficult, and this is where the SQUID amplifiers come in. Although Clark had built SQUIDs to work up to frequencies of 100 MHz, none had worked in the gigahertz frequencies needed. So he had to build one and then adapt it to meet the Axion dark matter experiment. Clark and colleagues showed that when cooled to temperatures of tens of millikelvin above absolute zero, the microstrip squid amplifier, or MSA, could achieve a noise that was quantum limited, that is, limited only by Heisenberg's uncertainty principle. This much quieter technology, combined with a refrigeration unit, reduced the noise by a factor of about 30 at 600 MHz, so that the signal from the axion, if it's there, should come through loud and clear. The Axion dark matter experiment team plans to slowly tune through literally millions of frequencies in the hopes of hearing a clear tone from photons produced by axion decay. Rosenberg says this result plants a flag, telling the world we now have the sensitivity and therefore a pretty good shot of actually finding the axion. And the important thing, according to Rosenberg, is that no new technologies or miracles are needed, just time. Fingers crossed. You're listening to Space Time. I'm Stuart Gary. Man's first attempts to touch the edge of space were very much a two-pronged effort. Captured Nazi V-2 rockets allowed scientists to get brief glimpses of space and see the curvature of the Earth's limb as these missiles travelled along their ballistic trajectories. But for longer duration scientific studies, researchers during the 1950s relied on high-altitude balloons to carry scientific payloads and even people to the edge of space. During the late 1950s and early 60s, explorers like US Air Force Colonel Joe Kittinger set world records of over 102,000 feet for high-altitude balloon flights in specially built gondolas and death-defying skydives. And even higher manned balloon flights in gondolas packed with scientific instruments were to follow. Eventually, it was US Navy Captain Malcolm Ross and Lieutenant Commander Victor Prather who took the Stratolab 5 gondola and balloon to a record-setting stratospheric altitude of 113,740 feet, or 34.67 kilometres. Now, think about that. This was a time before the first manned space flights. This was as close as humans could get to space. At 10 million cubic feet, or 280,000 cubic metres, the balloon envelope was the largest ever launched, expanding out to a diameter of 300 feet, or 91 metres, when fully inflated. Their primary objective was to test the Navy Mark IV full pressure suit. Developed by B.F. Goodrich using neoprene and weighing less than 10 kilograms, the Navy Mark IV was designed for use by high-altitude fighter pilots. and it was eventually selected for NASA's Mercury astronauts over a competing spacesuit developed by the US Air Force and used by pilots flying the X-15 rocket-powered spaceplane. Of course, technology's moved on a long way since those flights of the 50s and 60s. In fact, the current manned balloon altitude record was set in October 2014 as nothing more than a publicity stunt for an energy drink company. By the way, the new record is 38,969.4 metres, which was set in the skies high above Roswell, New Mexico. But despite the occasional publicity stunt, high-altitude balloons are still commonly used for scientific exploration, as explained in this month's issue of Australian Sky and Telescope magazine by the magazine's editor, Jonathan Nally.
So people think of astronomy with telescopes stuck on tops of mountains, or you might think of telescope in space, like the Hubble Space Telescope. But there's another way of doing it as well. In fact, it was one of the earliest ways of doing investigations of the sky, and that is to send telescopes and other instruments up on very high-altitude balloons.
Yeah, NASA used to do that from Alice Springs in central Australia. Now they seem to have moved those operations to New Zealand.
Yeah, they're doing it from New Zealand. They do it from Antarctica. They've done some from South America. They have done from Australia, as you say, in conjunction with the Australian Defence Force Academy and Professor Ravi Sood there, who was basically the Australian leader, the sort of leader at our end of things. I don't think it's certain that they won't ever do it again from Australia. You know, it all depends on what they want to do, what they want to look at, and how far they want the balloon to drift and all that sort of thing. Because what happens is, now these are high-altitude balloons. These are not hot air balloons, those pretty things that people go on joy flights in. These are really super special balloons. They're very, very, very thin plastic.
Mylar, isn't it? Similar to the stuff freezer bags are made out of.
Yeah, exactly. It's probably thinner than a freezer bag. In fact, it's very, very thin because it has to be big and therefore not too heavy. And when it's fully sort of inflated and it's up to size, it's basically almost see-through. You wouldn't even see it. They fill them with helium, and it doesn't have to be much. And they launch it from a special cradle on the ground. They put a bit of helium in, and they've got to get the winds just right, because this thing has got a lot of sail area. So if the wind is too high, it could just take off. So it's beneath the balloon is a big, like a crate with instruments on board, whether it's a telescope or something else, and that can be very heavy. You know, that can weigh a ton, and that's all attached to a truck. And what happens is, when they're ready to launch, they put a bit of helium in the balloon, and then they sort of point it all into the wind or away from the wind, whichever way you want to do it, and then the truck sort of takes off and takes this thing along with it, and then as the wind picks it up, it floats up into the air and the truck releases it. It's actually quite a dangerous operation. These people have come to grief. I don't think there have been any deaths, but trucks have been turned over. I mean, these are heavy prime mover trucks, have been literally turned over, head over heels, when the wind has caught the balloon in the wrong way. But assuming everything goes well, the balloon gets up to very, very high altitudes. Now, we're talking up,
120,000 feet. Yeah.
35 to 42 kilometres up, it's really, really high. Now, why they do that is this. Astronomers don't like looking through the atmosphere. The atmosphere blurs the pictures from outer space. The atmosphere...
and there are some wavelengths that you just can't see through the atmosphere.
Yeah, they absorb some wavelengths. So, I mean, the gold standard of doing astronomy is, of course, to put a telescope in space, like the Hubble Space Telescope and many others. But that's really expensive. But if you can get it up there above into space, into orbit, then you are, obviously above 100% of the atmosphere, essentially. When you've got a telescope on top of a mountain range, you're still only above about 50% of the atmosphere. Okay, so you've still got to look through a bit of murk. But if you can get a balloon up to these 30, 40 kilometre heights, you are above 99% of the atmosphere. So you can do it for a fraction of the cost of the space telescope. And the great thing about putting a balloon up and doing it this way is that you can send it up to do a test, and then bring it back down again and do whatever you need to do to adjust it and send it back up again. Because once you put something up into space, that's it. You can't really do anything. They did it with the Hubble a few times, but of course the space shuttle's gone now, so they can't do that. So these balloons, when they are inflated, they're called super pressure balloons. They're huge. They're 140 metres in diameter at their widest point. That's as wide as the Melbourne Cricket Ground. Right? In fact, the balloon would be about the size of the Melbourne Cricket Ground. It's just enormous. And these balloons go very high up, and they get way up where the winds are very high, and they can actually go all the way around the Earth. And they're sending their data via satellite these days, data back to ground control. And yeah, they can drift all the way around the planet, which is great. And then it comes back to where you have your landing ground, which is usually just somewhere in the desert or in the wilds of Antarctica. And a radio signal is sent. The instrument package that's dangling below the balloon, actually they sort of release a flap on the balloon deflates, and down it comes, a parachute pops out, and the whole thing floats down to the ground, and fingers crossed, if it all goes well, it doesn't get too shaken up when it hits the ground. It should be at a gentle speed of about 7 kilometres per second. Sorry, 7 metres. 7 kilometres. 7 metres per second.
This is how they handle the ice package that is now up on the International Space Station too. It started as a balloon experiment lifting off from New Zealand, and after a couple of goes they got it pretty well where they wanted to, and now they've sent it up to the International Space Station.
Precisely right. As I was saying, you can do your tests at a much lower cost by using balloons, and then when you've got the whole thing working the way you want it to, and you've proven the idea, then you can put it up on a satellite, and you know it's going to work. So, this is really interesting stuff. So we've got a great article all about balloon astronomy. Incidentally, the first balloon flight was in 1783. A couple of blokes, Jean-Francois Pilatre and Pilatre de Rosier, if I pronounced that correctly, and Francois Laurent, and they travelled 9 kilometres, right? That was a hot air balloon. 2 weeks later was the first hydrogen balloon flight. A guy called Jacques Charles. He went up to 3,000 metres, and 400,000 people turned out to see this amazing first hot air hydrogen balloon flight. That was in 1783. Can you imagine?
Been flying a lot longer than powered flight, haven't we?
We certainly have, yeah. And these were brave people. These were very brave people because, we went up to 3,000 metres. That's about 10,000 feet. You get up there, you really do need, if you're going to stay up there for any length of time, you need oxygen. If you go up and down pretty quickly, you're okay. But no one knew what was going to happen. No one knew whether people could go up that high and still live. They didn't know if the balloon would burst or break or burst into flames or whatever. So these were real brave people. So, I've been doing it for a long, long time, 1783.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. I'm Stuart Gary. You're listening to Space Time. Gamma rays are the most energetic forms of electromagnetic radiation and are emitted by some of the most powerful events in the universe. Now, a team of astronomers have just published 14 papers in a special issue of the journal Astronomy and Astrophysics covering some 15 years of gamma ray observations of the Milky Way. This massive data set will serve as a huge reference source for the international scientific community. Using an array of telescopes in Namibia, scientists with the HESS collaboration have studied populations of pulsar wind nebulae and supernova remnants, as well as microquasars, never before detected in gamma rays. These studies are supplemented by precise measurements such as those of the diffuse emissions from the centre of our own galaxy, including the giant gamma-ray Fermi bubbles extending far above and below the galactic disk. This new Galactic Plane Survey catalogue is 4 times larger than the previous one, dating from 2006, providing an immense reference source for the entire astrophysical community, who will for the first time be able to access a very high-energy gamma-ray data set of this size. It provides an overview of 15 years of research that has successfully characterized the most abundant types of gamma-ray sources, such as pulsar wind nebulae and supernova remnants, in the process making detailed measurements of individual sources as well as entire regions of the Milky Way. HESS has also revealed in detail the accelerations of particles that underlie these sources and how cosmic rays travel through the interstellar medium and shape their environment. In the universe, cosmic ray particles are associated with galaxy clusters, supernovae, binary star systems, pulsars, and certain types of supermassive black holes. The array's 5 telescopes have now identified 78 cosmic ray sources emitting very high-energy gamma rays, more than all the world's other observatories combined. Though a still poorly understood mechanism, cosmic rays attain their very high energies made visible by the emission of gamma rays. When these gamma rays reach Earth's atmosphere, they are absorbed, producing a short-lived shower of secondary particles that emit weak flashes of bluish light known as Cherenkov radiation, lasting just a few billionths of a second. It was in order to detect these extremely short flashes, and hence the gamma-ray emissions that cause them, that 14 countries combined to set up the HESS Array, the world's largest gamma-ray observatory. Built in Namibia in 2002, the HESS Array is made up of 4 13-metre and 1 28-metre telescope. The large mirrors of its 5-telescope array collect Cherenkov radiation and reflect it onto extremely sensitive cameras. Each image provides the direction of arrival of a gamma-ray photon, while the amount of light collected provides information about its energy. By building up images photon by photon, HESS can thus map astronomical objects in gamma rays. The telescopes have surveyed the Milky Way over the past 15 years, searching for sources of gamma-ray radiation. In spring 2003, the centre of our galaxy and the remnants of the explosion of a massive star were the first two sources identified by the Cherenkov telescopes during their testing phase. Since then, in some 2,700 hours of observation time, the array has continuously explored the galaxy, discovering many other sources and types of gamma rays, extending the field of ground-based gamma-ray astronomy ever further. For the first time, they've been able to classify celestial objects using only the emission of gamma-ray radiation. Most of these are supernova remnants generated through the violent death of massive stars. In addition, HESS has also detected emissions of new classes of objects emitting very high-energy gamma rays, such as stellar mass black holes in binary systems orbiting massive stars. And it's characterized the absence of emissions from other classes of objects, such as rapidly moving stars. The collaboration has been interested in sources of extremely high-energy gamma-ray radiation in the tera-electron-volt energy range, that is, energies in the range of 10 to the power of 12 electron volts, corresponding to 1 trillion times the energy of visible light photons. So far, the project's identified over 200 sources of tera-electron-volt radiation, both within and beyond our galaxy. Astronomers can often relate the extreme gamma-ray radiation detected by HESS to known astrophysical objects that have been studied before with conventional telescopes in lower frequency bands, such as optical and radio waves. Interestingly, however, HESS survey observations along the galactic plane of the Milky Way have identified many new sources not thought to be associated with objects seen at lower frequencies. The problem is the tera-electron-volt gamma-ray data alone is usually not sufficient to attribute a source to a specific type of astrophysical object. Consequently, these unidentified sources will, for now at least, remain a mystery in gamma-ray astronomy. Still, many other previously unidentified tera-electron-volt gamma-ray sources were eventually classified with a high level of probability as being supernova remnants. A supernova remnant is a debris field left behind by a supernova explosion of a massive star at the end of its life. The matter that's expelled in such an explosion generates shock waves that propagate through the interstellar medium. There, matter is heated and particles are accelerated to relativistic speeds. These particles then interact with light and gas in the neighbourhood of the source, generating very high-energy gamma rays. Over the last decade, scientists have identified about 300 known supernova remnants in our galaxy, which is shining very brightly in tera-electron-volt gamma rays. But all these objects were known before from observations in other wave bands and were classified as supernova remnants as a result of those observations. The question remains as to why these new potential supernova remnants have escaped previous detection. Though they cover an area of the sky as big as the full moon, they're apparently totally invisible to the eye or to conventional optical telescopes. Scientists think their location in the Milky Way and their large size may make them appear indistinguishable from other objects around them, or alternatively, they're simply being obscured by foreground gas and dust clouds. Of course, a more exciting possibility would be if these new supernova remnants are substantially different from other known types of supernova remnants which have been previously investigated by the HESS team. And that means they may belong to a special type of supernova remnant whose gamma-ray emissions are being induced by hadrons. I'm Stuart Gary. This is SpaceTime. The most powerful version of the Atlas V rocket, equipped with no fewer than 5 strap-on solid rocket boosters, was needed to provide enough thrust to lift the United States Air Force Space Command's AFSPC-11 mission into orbit. The United Launch Alliance Atlas V 551 blasted off from Space Launch Complex 41 at the Cape Canaveral Air Force Base in Florida, carrying the CBAS and Eagle spacecraft into geosynchronous transfer orbit using a complex 7-hour, 3-engine burn flight profile to deploy the 2 payloads directly into their planned 35,786-kilometre high orbits.
ECS reduced for launch.
Roger.
25.
Status check.
Go Atlas. Go Centaur.
Go App Space 11.
T-minus 10, 9, 8, 7, 6, 5, 4, 3. We have ignition. 2, 1, and liftoff of the United Launch Alliance Atlas V rocket with App Space 11 from the United States Air Force.
180 pump speed and injection pressure. Good chamber pressure across all 5 SRBs. The PU's gone to closed loop control, now passing 20 seconds into flight. Continue to see good pump speeds and injector pressures on the RD-180, 30 seconds in, and vehicle's now passing Mach 1. SRB chamber pressure continues to look good across all 5 SRBs.
You are hearing the
now
voice
passing
of
max
Patrick
Q,
Moore
maximum
providing
dynamic
launch
pressure.
vehicle ascent data.
And pump speeds and injector pressures on the RD-180 continue to look good. SRB chamber pressure is also looking good. Now passing 1 minute into flight. And the launch vehicle is now 11 miles in altitude, 7 miles downrange distance, traveling at 2,300 miles per hour. 1 minute, 15 seconds into flight, and we should be expecting SRB burnout momentarily. Chamber pressures on the SRBs tailing off, and we have burnout on all 5 SRBs. 1 minute, 40 seconds into flight. RD-180 pump speeds and injector pressures look good in full thrust mode, and we have good jettison of all 5 SRBs. Vehicle's gone to closed loop guidance, now passing 2 minutes into flight, Mach 5. And pump speeds and injector pressures on the RD-180 continue to look good. Vehicle is now 40 miles in altitude, 55 miles downrange distance, traveling at 4,900 miles per hour. And now passing 2 minutes, 30 seconds into flight. Approximately 2 minutes remaining in the Atlas booster phase of flight. And the RD-180 is now throttling down to maintain a constant 2.5 G acceleration limit. Engine response and vehicle acceleration response looks good. And the RCS pyro valve is unfired. Reaction control system is now pressurizing the flight levels. Now passing 3 minutes into flight. And seeing good response on the RD-180 pump speeds and injector pressures as vehicle throttles down to maintain that acceleration limit. And we have good indication of payload fairing jettison.
The primary payload is the Orbital ATK-built CBAS wideband extremely high-frequency telecommunications satellite. This is part of a US Air Force communications system independent of the US Navy's MUOS and National Reconnaissance Office SDS networks. The secondary payload aboard the flight was the ESPA Augmented Geostationary Laboratory Experiment, EAGLE, a technology demonstrator satellite also developed by Orbital ATK, which carries up to 6 independent experimental payloads on a common adapter ring with its own solar array and hydrazine-based minor propellant propulsion system. EAGLE was attached directly to the primary payload by Orbital's EELV secondary payload adapter. Good to see the system's finally working. The mission marked the 77th flight of the joint Boeing-Lockheed Martin Atlas V launch vehicle. The next flight slated for the Atlas V will be on May 4th, with NASA's Mars InSight lander mission to the surface of the Red Planet. This flight will also be the first mission to Mars to launch from the Vandenberg Air Force Base in California. In August, another Atlas V, this one equipped with a dual-engine center upper stage, will carry out the first unmanned test flight of Boeing's new Starliner spacecraft, which will eventually shuttle crews to the International Space Station. Meanwhile, Moscow's big heavy-lift launch vehicle, the Russian Proton-M, has made its first flight in over half a year, placing a new military telecommunications satellite into orbit. The Proton, carrying the Blagov S12L satellite, was launched from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan. The name Blagovest, meaning good news in Russian, will be dumped once the spacecraft becomes operational, when it will be renamed the Cosmos 2526. The Blagovest 12L is the second of a new generation of dual-use telecommunications satellites for Russia's military forces. They're designed to carry commercial telephony, broadcasting and internet services, as well as Ka and Q-band transponders linking Russia's military bases. When complete, the Blagovest constellation will consist of at least 4 satellites in geostationary orbit. First member of the new class, the Blagovest 11L, was launched back in August 2017, and later renamed the Cosmos 2520 once it became operational. You're listening to Space Time. I'm Stuart Gary. And time now to take another brief look at some of the other stories making news in science this week with a science report. And in a move that's been slammed by environmentalists and scientists, the Northern Territory government has announced plans to lift the ban on fracking. Fracking is the process of injecting liquids at high pressure into subterranean rocks or boreholes to force open existing fissures in order to extract oil or gas. Associate Professor Gavin Mudd from the School of Civil and Infrastructure Engineering at RMIT says fracking deserves to be controversial, both because it increases greenhouse gas emissions and because it poses significant pollution risks to the surrounding environment, which will need to be managed during the exploration and development phases. He says while the scientific inquiry into fracking has acknowledged these risks, the Northern Territory government has not. Meanwhile, Professor Jennifer McKay from the School of Law at the University of South Australia says most Australian governments have adopted a precautionary principle which would suggest that uncertainty in the science is a reason not to go ahead with environmental activities that have a risk. She warns that several human rights instruments could be infringed in the event of contamination of aquifers and surface waters as a result of fracking fluids. Scientists say a high-fat diet may help in the fight against a deadly mange killing off wombat populations in Tasmania. The findings, reported in the Journal of the Royal Society Open Science, are based on studies showing that infected wombats simply aren't eating enough to sustain themselves. Over the past 7 years, sarcoptic mange has killed off some 94% of bare-nosed wombat populations across parts of northern Tasmania. And the disease, which is caused by skin-burrowing parasites, has affected more than 100 species worldwide. It's hoped that if the new high-fat diet treatment proves successful, the findings can also be applied to other species. New computer simulations suggest that Neanderthals got their distinctive long face and rugged looks thanks to chilly conditions and a lifestyle that required a lot of energy. Neanderthal faces protrude a lot more than those of Homo sapiens, modern humans. But exactly why that's the case has been somewhat of a mystery. To resolve the issue, scientists used three-dimensional computer modelling to develop an accurately engineered reconstruction of a Neanderthal skull. The findings, reported in the Proceedings of the Royal Society B, show that despite popular belief, Neanderthals weren't especially strong biters, a finding which dismisses the possibility that Neanderthals' jaws evolved to give them a high bite force. But the hominids did have an impressively wide nasal passage, allowing them to inhale a lot of air at a time, suggesting a high-energy lifestyle. Plants are split into broad categories depending on how they process carbon, with the two main groups being C3, which includes trees, rice and wheat, and C4, which covers most grasses, including corn and sugarcane. It was always thought that C3 grasses would be more sensitive to carbon dioxide levels, allowing them to grow more rigorously as CO2 levels in the atmosphere increased. However, a new 20-year study reported in the journal Science suggests this is only a short-term effect. Instead, the authors found that after 12 years, the patterns reversed, with C4 ramping up their growth. This long-term information is essential in order for scientists and farmers, for that matter, to understand the future distribution of plants on a planet with increased CO2 atmospheric levels. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more Spacetime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.